Ever wonder how your bank can pull up your account balance in like a split second? Or how a social media app instantly knows every single one of your friends? Well, it all goes back to this incredible idea from the 1970s that brought some beautiful, elegant simplicity to a world of absolute digital chaos. It's called the relational model, and believe me, it completely changed how we deal with information. I mean, that's really the question of our time, isn't it? We are swimming in data, just oceans of it. But how do we actually make sense of it all? How do we ask a simple question and get a straight answer without having to navigate some kind of insane digital maze? Because before the systems we have now, getting an answer was like navigating a maze. This code here, it gives you a little taste of that complexity. This represents an old way of thinking, where a programmer had to literally spell out every single step for the computer. Go here, turn left, grab that piece of data, now go check that other thing over there. You want to ask a new question? Well, you had to go back and code a whole new path through the maze. It was rigid, it was complicated, and just incredibly inefficient. So yeah, let's just step back in time for a second into what I like to call the old data maze. Before this big revolution we're about to talk about, data was basically trapped. It wasn't like a library you could just browse through. It was this complex labyrinth where really only the original programmer knew the secret pathways.
Think about it this way. The data itself and the programs that needed to use it were basically welded together. You couldn't just ask the data a question. You had to follow these predefined paths. So if you changed your mind or thought of something new you wanted to know, too bad. It meant a huge rewrite. This was the massive problem that was just begging for a solution.
And then, right in the middle of all this mess, a brilliant mind over at IBM comes along with an idea. An idea so simple and yet so unbelievably powerful that it would become the foundation for pretty much all modern data systems. This was Codd's simple solution. So let's meet the man himself, Edgar F. Codd. He was a former pilot in the Royal Air Force, and, he brought this incredible clarity of thought to the very messy world of data. He proposed a completely new way of thinking, and for that, he would eventually go on to win the Turing Award, which is basically the Nobel Prize of Computer Science. And this was his whole philosophy. Codd believed the computer should handle all the complexity, not the person trying to get an answer. The user should only have to describe what they want, not give a detailed map of how to get it. And his entire model was built on this one powerful, beautiful principle. So here it is, the revolutionary idea. Codd said that all data, no matter how complex it seems, could be stored in simple tables. Yeah, just like the spreadsheets we use every single day. He called these tables relations. Each table has columns for different things, like a name or an age, and rows for each individual record. That's it. No complicated pointers, no tangled paths, just clean, independent tables. And to really get why this was such a big deal, let's look at some other ways to store data. You've got key value stores, which are kind of like a simple digital dictionary. Then you have semi-structured models, which are super flexible but can get, well, messy. The relational model, right there in the middle, forces everything into this clean, predictable grid. And you know what? That structure, that rigidity, is its superpower. Okay, but having data in tables is only half the story, right? The other half is the amazing toolkit Codd created to actually work with them. This toolkit is called relational algebra, and you can think of it like a set of Lego blocks for your data. The first tool in the box is called selection. It lets you filter rows based on some condition you set. The easiest way to think about it is you're taking a horizontal slice of your table, keeping only the rows you care about. So let's use this simple user table as an example. We've got a user ID, a name, their age, and some kind of popularity score. Pretty straightforward. Now, if we apply a selection and say, hey, only show me users with a popularity greater than 0.5, boom, we get this. We've just horizontally sliced the table, keeping only Bart and Lisa. The other rows? Gone. Filtered right out. Simple, clean, and fast. So our next tool is called projection. And if selection was a horizontal slice, you can probably guess that projection is a vertical slice. It lets you pick and choose exactly which columns you want to see. Let's try this on our user table. If we say, just project the UID and name columns, this is the result we get. See that? We vertically sliced the data, completely ditching the age and popularity columns to focus only on the information we actually need right now. Now, slicing up a single table is useful for sure, but the real magic, the real magic, happens when we start connecting information across different tables. This is where the true power of this whole model just gets completely unlocked. And that brings us to the most powerful tool in the entire kit, the join. This is the operator that lets us connect the dots. It lets us combine two totally separate tables into a new one, based on a column they happen to share. And this is the genius of it all. We can keep our data in small, clean, logical tables and then weave them together only when we need to ask a question. Okay, let's see this thing in action. On one side, we've got our good old user table. On the other side, we've got a brand new member table, which just links user IDs to the groups they belong to. The key here, the critical part, is that they both share that UID column. That's our bridge. So when we perform a join on that shared UID column, check it out. We get this brand new, wider table, and now all of a sudden we can see the user's name right next to the group they're in. We've instantly connected the dots between two separate facts. This is absolutely fundamental. And now we can start snapping these simple operators together to answer some really complex questions. So let's try something tricky. Who is in Lisa's groups? We can build a plan just like this. First, we select Lisa from the user table to get her ID. Then, we join that with the member table to find her groups. After that, we join again to find all the other members of those same groups. And finally, we join back to the user table to get their names and project just the names for our final result. Each step is just one simple Lego block, but when you put them together, they build a powerful, precise answer. So, okay, we have these neat tables, we have this logical toolkit, but why did this 50-year-old idea completely change the world? Well, the answer comes down to a powerful mathematical guarantee. It all comes down to the big one, Codd's theorem. What Codd did was he mathematically proved that the step-by-step how-to language we just explored, the selections, the projections, the joins, was perfectly equivalent to a much simpler language for just describing what you want. And that was the game changer. It meant for the very first time you didn't have to tell the computer how to find something, you could just describe what you were looking for, and you were guaranteed that the computer could figure out the best, most efficient step-by-step plan all by itself. And that incredible discovery created a direct line from his 1970 paper to the world we all live in today. Relational algebra provided the powerful engine, the how-to, and that allowed for the creation of declarative languages like SQL, the language pretty much everyone uses to get data today. You just tell the database what you want, and thanks to Codd's brilliant work, it knows how to find it for you. So, Codd's model gave us this incredibly powerful way to organize structured, predictable information. It really did bring order to the chaos, but it leaves us with a fascinating question for our modern world. In an age of messy social media posts, unstructured videos, and complex sensor data, what happens when our data doesn't fit so neatly into tables?